everybody, it's Doc again. Someday I'm going to switch out and have somebody else do this. Day 2, Calc 1, Lesson 5, Section 1-5. If you have the other book, which I don't advise you getting instead, but if you had to for whatever reason, it's 2.2. Okay, so we're going to be working a lot out of the book again today. Looking at the same concept that we ended with before, is finding the limit of a function. And here we're going to have our table of values. So let's take a look right here at this polynomial. And we want to look at the table of values near the number 2. So we're going to look at how it approaches it from the left. And we're going to look at how it approaches it from the right. So how it would approach from the left, we can start at 1 and work our way up to 2. We put those values into this equation, f of x, or y equals, right here. And these are the values that I will get for my y values. If I do the same thing, but this time I'm approaching it from the right, I'm starting at 3 and I'm going down to closer to 2. I will get these values. So the bottom line of the question is there a certain value that both of those get closer to? Okay, so when we look at both sides, we can see that when it's coming from the left, it gets really close to 4. And when it's coming from the right, it also gets really close to 4. So by observation, we say, and using the table, we would write it as the limit as x approaches 2, put the function that is in question, that will equal 4. And we can make that, we can give that conclusion based on the data that we have in our table on both sides coming closer and closer to 4. So let's look at a definition. Suppose f of x is defined when x is near a number a. So we have some kind of graph, but there's a specific point A that we're interested in. We want to find out what the limit is at that point. And what we will do then is we're going to say that the limit as x approaches a of f of x equals L. So that's how we properly say it. The limit of f of x as x approaches a equals L. Okay? All right. This is a long, sorry, it's not going to be a short one today. This is a long section. So let's move right along. Now, the one thing that you should really pay attention to here in that definition is that it said as x approaches a, not as x equals a. We are not talking about the value at a. And that's very important when we're talking about limits, is that you're not just assuming it is the value at a. You're looking at it as it approaches a. So, for instance, I could have this graph here, which is a continuous graph. It has no breaks in it. And I do have a specific value at A. So when I approach from both sides, I'm going to get close to that value. The same value at A. However, I might have a graph that looks like this, where at the value at A actually drops and it's a point somewhere else. So I don't want to use this as my limit because it's sure not in pattern with what I'm looking at. So I want to find the limit as it approaches this. And as it approaches this, what does it get close to here? Not the actual value. And then sometimes we might have a graph where we have a hole there and we just don't have a value there. It's not defined at all at A. When it's not defined at all at A, then that wouldn't help us much. So that's why looking coming from the left and looking at coming from the right is very helpful, because then it can give you the value that it's getting close to. Okay, example 1. We're going to guess the value of this limit, and we're going to use a table of values. Now, where are we guessing it at? As it approaches 1. As it approaches 1. So, I want to make a table of values. I want to pick values that are smaller than 1, and I want to pick values that are bigger than 1, but that get close to 1. So let's start at 0.5 and work our way to 1. This would be coming from the left to the number. How about looking at 1.5, which would be on the right of it, and coming towards 1? By looking at both tables, we can see that both of the values seem to be getting really close to 0.5. Enough, in fact, that we are comfortable with saying the limit of x minus 1 over x squared minus 1 as x approaches 1 is 0.5. So the limit as x approaches 1 of x minus 1 over x squared minus 1 is 0.5. Now, this is an example of where we looked at before. If I tried to put 1 into this equation to see what the value is at 1, it would be undefined. That's because I have this curve coming down here, and when I place 1 in the denominator, I will get 0. So it's just open. No point there. Okay? So again, that's why it's important to understand that we're looking at getting close to A and not A itself. Let's move on to example 2. We're going to estimate the value as time approaches 0 of this function. Looks a little complicated. We're going to use a table of values. Now, this table of values will give you plus or minus 1, plus or minus negative, or plus or minus 0.5, plus or minus 0.1, plus or minus 0.05, plus or minus 0.01. And the reason is that this graph is a symmetric graph. So the values are going to be the same height-wise. It's just one's going to be negative and one's going to be positive. And we're looking at it as it approaches 0. So when I look from the left into the right, at 1, I get 0.16228. And this is just plugging these numbers into here and computing those in your calculator. And I continue to do that. It looks like it gets closer and closer to 0.16667. So we can kind of guess from that this limit as it approaches 0 is actually going to be close to 1/6, which is a value 0.16666. The question is, do we get small enough when we look at this? We went to the hundreds place, but what if we would have gone to thousands place or 10,000s place or even the millions place? What if we would have done that? Here we have 0.005, 0.0001, 0.00005, and 0.00001. Now again, it's a symmetric graph, so you're going to get the same height value on your y. And we can see when we do this that something kind of strange kind of happens. It has 1.6800, kind of goes up, and then it goes up high, and then it goes down. So something's really odd. So this is where we have to be careful, because we can get a false value if we're not picking the correct numbers. This is an interesting problem, because if you put this into your graphing calculator, if you have a graphing calculator, put this into your graphing calculator and make your window -5.5 by -0.1, 0.3. Go ahead and pause this and do that. When you do that, you should get a curve that looks pretty smooth. Now, if you zoom in a bit, you'll see that that doesn't look so curvy now. It's almost a straight line. And if you get even smaller, you can see it actually really fluctuates around the origin. So let's dive into it really small. And we see we have this here, and that's at -10 to the -7, 10 to the -7 by 0.1, 0.3. Now, I'm not going to say that this is going to happen in a lot of them. You have to look at this. Now, this is kind of a strange function. It's an algebraic function, if you remember. It has a root function in it. So whenever you have square roots and other things going on in the algebraic function, you want to be extra cautious about assuming what your limit would be. Here's another example. The limit as x approaches 0 of sine x over x. This is approaching 0. We're going to make a table. Again, this is a symmetric function. We're looking at it about 0 as it approaches 0. So the sine function is going to be symmetric on both sides. So at x equals 1, it's going to be here. At x equals -1, it's going to be here. See how they're the same height? And then as I go in 0.5 and 0.5, they're the same height. So that's why it says plus or minus 1, plus or minus 5, because you get the same y values. And we keep going, and we go pretty small. We're at 0.001. And it looks like for this value, it approaches 1. So we would probably say that the limit of this function is 1. And not only there, but we have to remember that it's a periodic function, so it depends on how far we want to look in our domain to see. Now, if I continue to look as I move on, 2 pi more, 10 pi more, 2 pi more, 4 pi more, I get 0. So I'm feeling pretty confident at this point that the limit as x approaches 0 of sine of pi over x is 0. However, not right. Look at that. It's really kind of a crazy function here when you take this value and you are dividing it by x right here. This is the pi over x. Okay, so from the data table we got this. We know that this can't be. We think that it goes probably close to 1. But now if we take a look at the second one where we have pi over x, and we're plugging our values in, and we're feeling like we're getting pretty close to 0, we notice that we're really not correct in that assumption, because this one has a very strange oscillating around the x-axis, up and down, up and down, up and down. So sometimes you might get the right answer as it approaches 1, and sometimes you're going to have to be careful depending on the function. Okay? How do you know? That's the big question. Well, being familiar with your functions does help. And sometimes it's just a matter of putting in a couple smaller numbers just to see if it's the same. For instance, over here, oh, so what's the answer? Yeah, I guess we got to discuss that. So if you have something that happens like that, like the other one that we looked at, you would say that there actually is no limit. The limit does not exist. When that happens and you're getting one value going one way, one value going another way, and it's going up, down, up, down, up, down, and you can't really set on a number, then the limit doesn't exist. So not everything has a limit. Let's look at this next one. Example 5. Here we have the function inside here. We're looking at x approaches 0. We have a table of values again. This time we're going to go to 0.01. And it appears that the limit would be 0. However, I look at it kind of close. I'm like, you know what? This cosine 5x is divided by 10,000. Maybe I want to zoom in a little more and see if it's actually getting close to 0 or not. And when I do that, I can see that it's actually getting closer and closer to 0.001, which is 1 over 10,000. So the limit isn't 0. The limit is actually 1 over 10,000. Now, as we've been stressing through this so far, we have been looking at how it approaches the limit from the left and from the right. There are some pitfalls in that, because, for instance, let's take a look at this. This is a graph named after Oliver Heaviside, who was an electrician, and he said the current is going to be 0, 0, 0, 0, 0, and then you flip the light switch on, and then it's 1, 1, 1, 1, 1, all the way across. So obviously, if I approach this from the left, and I approached it from the right, I'm going to get two very different numbers. So that came the discovery of sometimes we need to just look at limits from one side. Whenever we're looking at limits from one side, we're going to use this symbolization. This means the limit as it approaches 0 from the left. And this means the limit as it approaches 0 from the right. If we go over here and look at this graph, we can see from the left, and I'm not sure if you can see that real well, but the graph actually goes here, open circle, and then closed circle here, and continues. So hopefully that's a little better. Okay, so if I look at it coming from the left, I can see that my numbers are going to be very close to 0. If I look at it from the right, I can see my numbers are going to be very close to 1. So when this happens, we can say that the limit as t approaches 0 from the left, by putting this negative here, of h of t equals 0. And the limit as t approaches 0 from the right of h of t equals 1. Now, what about from both sides? Well, when you're looking at one-sided limits, to say what is the limit overall as t approaches 0, like we've been looking at before. When these two are not the same, that limit does not exist. Does not exist. DNE. Okay? Looking at a couple of those definitions. Here we have the left-handed limit. The limit as x approaches, the limit as x approaches a from the left of f of x is equal to L. So left-handed limit of f of x as x approaches a, or the limit of f of x as x approaches a from the left, whichever way you want to say it, is equal to L. Okay, so definition 2 differs from definition 1, and only we require a to be less than a. It has to go in one direction. If we do the right-sided limit, then we're going to be looking at it as it approaches greater than the number. Okay? So because we're looking at the left-sided limit, we're only going to be looking at the value smaller than. If we're coming from the right, it's going to be greater than. All right, so here's some examples of that. We have an a value here. We have a function. We want to find the limit right here, this function. So obviously we're not going to do anything on this side because there isn't even a graph. So I'm going to look at all these values as it approaches a from the left. Over here, similarly, we have a graph. We want to find the limit here, so I have to approach it from the right. And I would write it, the limit as x approaches a from the right of f of x equals L. Now, the big one. I mentioned it already. You have the limit of f of x as x approaches a is equal to L. If and only if and only if the limit of x as it approaches a from the left and the limit as x as it approaches a from the right are also L. So these have to be the same thing in order for the entire limit to be equal to that. What am I talking about? Well, let's look at the graph. Okay. Here we have a graph of this function, g of x. It comes up, drops down, and comes around. Has a couple places here where it's undefined. Can you see that? I'll make the circles a little bit bigger. Undefined here. Okay. So let's take a look at what the limits would be. We want to look at the limit as x approaches a, or I'm sorry, as x approaches 2 from the left of g of x. And then we want to look at the limit as x approaches a, or as x approaches 2 from the right of g of x. And then we want to compare those to see if there is a limit at x approaches 2. Well, I look over here and I notice that's where my break is. So there's a big hint that probably the limits are not going to exist. But I might not have the graph right in front of me. Here we're using the graph to find the limit. So we're going to have the limit as x approaches a from the left. I'm going to go to it from the left. And what do I see it approaching? It approaches 3. Now I do the same thing from the right, and when I do it from the right, it approaches 1. Well, 3 and 1 do not equal. And since 3 and 1 do not equal, that means the limit as x approaches 2 of g of x does not exist. So I'm going to put that up here because squeezed it over here in the corner. But the limit as x approaches 2 of g of x does not exist. So we're not getting the same value. All right, let's look at D. We're looking at 5 now. So we go over to 5, and we see what values am I going to get as I approach 5. Well, when I approach it from the left, I get a value of 2. When I approach it from the right, I get a value of 2. Even though my value here, I have a solid dot down here at, looks like a little more than 1, I'm ignoring that because I'm looking at the limit, which is what it's approaching and not what its value is. So since from approaching from the left, I get the value of 2, and approaching from the right, I get the value of 2, and those are the same, then that means that I can conclude that my limit as x approaches 5 of g of x is in fact 2. Okay? My limit is in fact 2. Okay, this is a long section, I warned you. The last one was short. All right. Infinite limits. What does that mean? Okay, let's say I start to approach something. I'm trying to get closer and closer to it, and my numbers just keep getting bigger and bigger and bigger. For instance, what if I have 1 over x squared? Does this exist as it approaches 0? Here's my graph of it. I can see as I approach it from the left that it's going to get bigger and bigger and bigger and bigger and bigger. As I approach it from the right, also bigger and bigger and bigger and bigger. When I put my numbers in, I have my plus or minus because it is symmetric, so they're the same height for positive and negative, so I can do that. I get the values 1, 4, 25, and then it shoots straight up. When that happens, it is an infinite limit. That means my result is going to be the limit as x approaches 0 of 1 over x squared is infinity. Now, this does not mean we regard infinity as a number. Again, infinity, we can never get to it. But it does tell us that it increases without bound, or maybe decreases without bound if it's going down. So, definition. Let f be a function defined on both sides of a, except possibly at itself. Then the limit as x approaches a of f of x can equal infinity, meaning that the values can be made arbitrarily large, or as large as we please, by taking it as close to a but not equal to a. They show you another notation for this is like this too. Really doesn't matter. Sometimes you'll see f of x as it approaches infinity that way also. So you might see some different notations. The limit of f of x as x approaches a is infinity. F of x becomes infinite as x approaches a. F of x increases without bound as x approaches a. This is probably the most popular one. For me anyway, I guess. Okay, here we have another one where we go from the left and from the right, and we see that it's getting bigger and bigger and bigger going up. So again, this limit would also be, as it approaches a of f of x, would also be infinity. Similarly, if it's going down, same thing, but now negative infinity. So here I have my graph. I have my asymptote, my vertical asymptote here. I approach it from the left, and I approach it from the right. And when I do that, I'm getting smaller and smaller and smaller numbers. So this time I say the limit as x approaches a of f of x is equal to negative infinity. Example would be here. Negative infinity. So, you can have the limit as x approaches a from the left of f of x is infinity. The limit as x approaches a from the right of f of x is infinity. The limit as x approaches a from the left of f of x is negative infinity. And the limit as x approaches a from the right is also negative infinity. Just some more examples here. This would be a one-sided limit coming from the left. This would be a one-sided limit coming from the right. This would be a one-sided limit coming from the left. And this would be a one-sided limit coming from the right. And just as before, if you get the same thing from the right and from the left, then you can say the limit of the function as a whole also has that. And there will be a vertical asymptote. Okay, now let's move on to example 9. Example 9, we're going to look at the limit as x approaches 3 from the right of 2x over x minus 3. And we're going to look at the limit as x approaches 3 from the left of 2x over x minus 3. So, we notice that as we get close to 3, that we're not going to have a value because we're going to get, if we put 3 in the bottom here, we will get 0. We can't have a 0 in the denominator. That's not defined. If I look at them individually, as it approaches from the right, then it looks as if it's going to positive infinity. If I approach it from the left, it looks as if it's going to negative infinity. So once again, we have a limit if we're going to look at the one-sidedness, and we do have a vertical asymptote going right through x equals 3. Another function that's similar to that would be the tangent function. We have all these vertical asymptotes. And if we look at the tangent, let's say here it says pi over 2. Look at pi over 2. Let's look at it coming from the left. As it comes from the left, it's going to get to positive infinity. Comes from the right, negative infinity. And you can see that will repeat. What about the natural log function? Let's look at the natural log function. Natural log function is a one-sided limit. Here's what it looks like. So we're not going to approach it from the left. We can only approach it from the right. And as we approach it from the right, we will see that it goes to negative infinity. So the limit as x approaches 0, and again, this sign just means the direction, from the right is equal to negative infinity. Okay, that was section 1.5, or 2.2 if you have the old book, which I don't recommend. because I'm not sure if the examples or the exercises in this book are going to be the same as the one that I assign you. And I will see you soon for lesson 6, which will be lesson 6 will be the last lesson for day 2.